The ratio and root test. Objectives. By the end of this lesson, you should be able to use the ratio test to determine if a series converges or diverges, and use the root test to determine if a series converges or diverges. The ratio test. Let the sum of a sub n be an infinite series. If the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1, then the series converges. If the limit of the absolute value of a sub n plus 1 over a sub n is greater than 1, then the series diverges. But if the limit of the absolute value of this ratio equals 1, then the ratio test is inconclusive, and the infinite series could either converge or diverge. So another test would be needed to decide the series. Now, the point I want to make here about the ratio test is that the absolute value bars means that this original infinite series could have been alternating. But when we include the absolute value bars, that's going to be irrelevant entirely whether or not the series was alternating, and we're really just looking at comparing the general term to the general term plus 1. So the a sub n plus first term over a sub n, and we're ignoring the fact that it is potentially an alternating series. Alright, so in these examples we want to use the ratio test to determine whether the following series converge or diverge. So off to the right here, I'm going to write what we need to look at. We need to look at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And we need to compare that to 1. So whether it's less than, greater than, or equal to 1. So less than, greater than, or equal to is what we're trying to decide right now. So this series has a general term, an a sub n, of 1 over n factorial. So we need to set up the limit as n approaches infinity of the absolute value of, so a sub n, the general term goes on the bottom. So 1 over n factorial goes on the bottom. And what goes on the top is a sub n plus 1. So in other words, n plus 1 is going to be substituted into this n. So on top is 1 over n plus 1 factorial, absolute value. Alright, so now we're going to do the limit as n approaches infinity. So right here, this is a fraction over a fraction. So instead of doing 1 over n plus 1 factorial over 1 over n, let's do 1 over n plus 1 factorial times n factorial over 1. Still in absolute value bars. So this is the limit as n approaches infinity of the absolute value of n factorial over n plus 1 factorial. Alright, let's think about this for a second. We want to try to figure out if this will somehow reduce. So let's plug in some numbers for a second just to get an intuition. What if I had 2 factorial, and the bottom, if I have n plus 1, well that would be 2 plus 1, so 2 factorial over 3 factorial. Well, 2 factorial is 1 times 2, and 3 factorial is 1 times 2 times 3. So what cancels out is the 1's and the 2's, and all I'm left with is 1 over 3. So similarly, the top part of this, and on this one example we'll go through showing all the steps here, the top of this is 1 times 2 times ... times n minus 1 times n, and the bottom part of this is 1 times 2 times n minus 1 times n plus 1. So in other words, everything on the top is going to cancel with almost everything on the bottom. The only thing left on the bottom is an n plus 1. And on the top, I'm just going to have a 1 left over. So what I'm really doing is evaluating the limit as n approaches infinity of 1 over n plus 1. So why did I drop the absolute value bars? Well, here I'm taking n values that approach infinity. So I'm only going to be plugging in here positive numbers. So the absolute value bars are a little bit redundant. So the limit as n approaches infinity of 1 over n plus 1 equals 0. Now, the ratio test says that if this converges to a number less than 1, then the original series converges. So converges by the ratio test. So it looks like a lot of work, but that's because we were going through the formal explanation of why this simplified down to 1 over n plus 1. So now let's take a look at the next example. And I'm actually going to go ahead and erase all this so we have room for the next example. Alright, so now I have the sum of n equals 1 to infinity of 3 to the n over n. Whoops, I don't want to write equals. That would have been a really bad thing to do. So this isn't equal to this limit. I'm just solving this limit to help use the ratio test. So I want to look at the limit as n approaches infinity of a sub n plus 1, so 3 to the n plus 1 over n plus 1 all over 3 to the n over n in giant absolute value bars. So now this is the same as the limit as n approaches infinity of 3 to the n plus 1 over n plus 1 times the reciprocal n over 3 to the n. And I'm going to go ahead and drop the absolute value bars at this step because everything here that we're talking about is going to be positive. And now I want to see if I can simplify things. So I am going to go through quite a bit of steps here just to justify everything. So this is the limit as n approaches infinity of 3 to the n plus 1 over 3 to the n times n over n plus 1. So all I did was switch the places of the denominators, which I can do because multiplication is commutative. Well, now the numerator is going to become 3 to the n times 3 to the 1, because if they have the same base, I can add their exponents. But the 3 to the n's are going to cancel out. So what I have left on the top, I have the limit as n approaches infinity. I have a 3 on top. I have an n on the top. The 3n on the bottom is gone, so I just have an n plus 1 on the bottom. So now this limit as n approaches infinity, and this limit at infinity, the degrees match, so my limit is 3. 3 is greater than 1, so by the ratio test, this original series way over here diverges. So now we've had an example of one where we're using the ratio test to determine convergence, and then this next example we have divergence. So now let's take a look at the third example. Alright, so I have the sum of n equals 1 to infinity of 1 over the square root of 2n. So I'm going to look at the limit as n approaches infinity of 1 over the square root of 2 times n plus 1. So remember, the a sub n plus first term over 1 over the square root of 2n. And we have absolute value bars around that quantity, which equals the limit as n approaches infinity. So when I multiply by the reciprocal here, this radical 2n is going to move to the top. And on the bottom, I have radical 2n plus 2. So I distributed that 2 inside. Alright, so here, if I think about this limit as n approaches infinity, well, this plus 2 here becomes pretty arbitrary once I start plugging in huge values for n. So the square root of 2n over the square root of 2n, well, that limit at infinity is going to go to 1. So, in other words here, the ratio test is considered to be inconclusive. So I can't determine anything from the ratio test because the limit of a sub n plus 1 over a sub n gave me exactly 1, and that doesn't tell me anything. So this original series might converge, might diverge. There's not enough information to tell. So let's keep going. Alright, in this next example, I'm going to go ahead and set up my limit. The limit as n approaches infinity, and everywhere there's an n, I'm going to put an n plus 1. So the top is going to be n plus 1, and the bottom is going to be n plus 1 squared over n plus 1 squared. All that in absolute value bars. So now this is the limit as n approaches infinity, and I'll have n plus 1 over n plus 2 squared times, so that was the numerator, and then I'm going to do the reciprocal of the denominator, so n plus 1 squared over n. Alright, and so now at this step, we really have to try to think about what's going on with this limit at infinity. So on the top, I don't want to have to go through the process of doing a lot of expanding here, so I don't want to expand n plus 1 times n plus 1 and FOIL it all out. The key is to recognize that the dominating term up here, if I were to FOIL everything out, would be an n cubed. And similarly, in the denominator, n plus 2 squared, well, I would have an n squared from that multiplied by this n, so the bottom is also n cubed. So the ratio test in this example is also going to be inconclusive because this limit at infinity, if the degrees match and the leading coefficients match, the answer is just 1. So the ratio test is yet again, inconclusive. Can't tell what happens by using the ratio test. So now let's go ahead and look at another example. I have the sum of n equals 0 to infinity of the quantity 2n factorial. So we're going to do the limit as n approaches infinity of 2 times n plus 1 factorial over 2n factorial. And all of this in absolute value bars. So now I have the limit as n approaches infinity. On the top I have 2n plus 2 factorial. So the 2 would distribute to both here over 2n factorial. And I'm dropping the absolute value bars because these quantities will be positive. So now the top is the limit as n approaches infinity. 2n plus 1 factorial, well, that would be 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, ... We're multiplying all out. So 2n plus 2 factorial would expand to this numerator. And then all over 2n times 2n minus 1 times 2n minus 2. So if we see what cancels out, the 2n and the 2n minus 1, and all of that part multiplied all the way down, these are all multiplied down, are all going to cancel with the entire denominator. So in other words, all that's left on the top is going to be, let's actually FOIL it out here, I'll get 4n squared plus 6n plus 2. So as n approaches infinity, this quadratic is going to go to infinity, which is definitely greater than 1. So by the ratio test, this series diverges. But was this the most efficient test to use? So because we're going to start building on our tests, it's important to first try the nth term test on any series that we don't automatically recognize to be geometric or telescoping. So if we would have done the limit as n approaches infinity of the general term, 2n factorial, well, this clearly is going to go to infinity. So remember, if this thing doesn't go to 0, then the original series definitely diverges. So this would have been the shortest method to determine divergence, although using the ratio test did also work to conclude that this sum does go to infinity. So the ratio test concluded that the sum diverges. And let's take a look at one final example where we apply the ratio test. So we have the limit as n approaches infinity of 2 to the n plus 1 over n plus 1 factorial. And here's what I'm going to do. I'm going to jump to writing multiply by the reciprocal already. So hopefully we'll get to that point where we don't actually have to do a sub n plus 1 over a sub n. We can do a sub n plus 1 times the reciprocal because most of our general terms are going to be fractions. So this would technically be in my absolute value bars. So now, how this is going to simplify, the limit as n approaches infinity, well, 2n plus 1, that's 2n times 2, so the 2n's will cancel. So in the numerator, all I have left is a 2 from these two parts. And now n factorial over n plus 1 factorial, well, we decided that the only thing left over was going to be an n plus 1, and that's going to happen in the denominator. So as n values approach infinity, The bottom of this is growing bigger, so this limit goes to 0, which is less than 1. So the original series converges by the ratio test. So here we have the sum of n equals 0 to infinity of negative 1 to the n times 5 to the n over n factorial. So here I'm going to go ahead and apply the ratio test. So I'm going to have the limit as n approaches infinity of the absolute value of negative 1 to the n plus 1, 5 to the n plus 1, over n plus 1 factorial. And then technically this is all over this same term, this a sub n, right? This portion here is a sub n, but that's the same, dividing is the same as multiplying by the reciprocal. So I'm just going to go ahead and multiply by n factorial over negative 1 to the n, 5 to the n in absolute value bars. So because the absolute value bars are here again, this negative 1 to the n plus 1 and this negative 1 to the n are becoming irrelevant. So what I'm going to go ahead and do in the next step is write the limit as n approaches infinity. So I'm going to leave out the absolute value bars and leave out the terms involving negative 1 to the n or n plus 1. And I'm going to put the 5 to the n times 5 to the 1 term. So 5 to the n plus 1 is 5 to the n times 5 to the 1 over 5 to the n. So I'm going to leave those two over each other. And then I'm going to put the n factorial over the n plus 1 factorial, just so I can see that now the 5 to the n's are going to cancel. And then here, when I have n factorial over n plus 1 factorial, hopefully we've seen that the n factorial will become 1, and the denominator will be just an n plus 1. So the remaining limit that I have is the limit as n approaches infinity of 5 over n plus 1, which as n approaches infinity, this limit goes to 0, which is less than 1. So by the ratio test, our series converges. So in other words, we could apply the ratio test even when there is an alternating portion to it, because the absolute value bars get rid of any term that is going to be negative. And now let's try this next one. So the sum of n equals 1 to infinity of n squared over 2n minus 1 factorial. Just for some ratio test practice, we have the limit as n approaches infinity. So here we get n plus 1 squared over 2 times, I'm going to replace this n with an n plus 1. So 2 times n plus 1 minus 1 factorial times, so there are absolute value bars here, the reciprocal of this. So instead of dividing by this term, I'm going to multiply by 2n minus 1 factorial over n squared. And now let's go ahead and simplify. The limit as n approaches infinity of, let's see, we'll put the n plus 1 squared over n squared over each other. And then here we're going to have 2n minus 1 factorial over, this portion would be 2n plus 2 minus 1. So in other words, this is going to be 2n plus 1 factorial. And we drop the absolute value bar. So now let's see what's about to happen. So the n plus 1 squared over n squared, as n approaches infinity, this portion here is going to go to 1. So now we kind of had to think about how this part's going to reduce. So 2n minus 1 factorial over 2n plus 1 factorial. So let's sort of expand the denominator here. 2n plus 1 factorial is 2n plus 1 times 2n times 2n minus 1 times 2n minus 2, etc. And the numerator would be 2n minus 1, 2n minus 2, etc. being multiplied. So on the top, all I'm going to have left is a 1. And on the bottom, everything 2n minus 1 and below will cancel, so the denominator is just 2n plus 1 times 2n. So that's going to give me, what, 4n squared plus 2n? So here, this is 1 over 4n squared plus 2n. So what's going to happen is as n approaches infinity, this portion is going to 1, but 1 over 4n squared plus 2n is going to 0, so this whole limit equals 0, which is less than 1. So by the ratio test, this thing converges. This infinite series converges. The root test. So let the sum of a sub n be an infinite series. If the limit as n approaches infinity of the nth root of the absolute value of a sub n is less than 1, then the series converges. If the limit as n approaches infinity of the nth root of the absolute value of a sub n is greater than 1, then the series diverges. And if that limit equals 1, then the root test is inconclusive. The series could either converge or diverge, and another test is needed to decide the series. So the reason the root test and the ratio test sort of go together is because they have the same conclusions. We're just evaluating a different limit. So this limit, the limit as n approaches infinity of the nth root of the absolute value of a sub n. But if that limit is less than 1, we have converges, greater than 1, diverges, equals 1, inconclusive. So again, the same conclusions as the ratio test. So let's go ahead and try the root test. Alright, so I have the series n equals 1 to infinity of negative 1 to the n over n to the n. Alright, so here we want to apply the root test, and what tells us that we need to apply the root test is that I have this n in the base and n in the exponent. So here I can't rewrite this to be a geometric series because I have this n to the n. So in order to get rid of an nth power, I can use an nth root. So what we're going to have to do is the limit as n approaches infinity of the nth root of the absolute value of negative 1 to the n over n to the n. Alright, so when I apply the absolute value, this is going to become the limit as n approaches infinity of the nth root of 1 over n to the n. Alright, so now our properties of radicals, or roots, tell us that I can do the nth root of 1 over the nth root of n to the n. Now the nth root of 1 is always just 1, so my numerator there is 1. And then here, this is n to the n, the inside. When I have an nth root of something, that becomes 1 over n. So notice what happens to the n times the 1 over n. So in this case, it goes away entirely. N times 1 over n just gives me 1. So this is the limit as n approaches infinity of 1 over n. So this portion here cancels out. And as n approaches infinity, this limit goes to 0, which is less than 1. So by the root test, and since we already used RT for ratio test, we should actually write out root test. This series converges. Alright, in this last example, I have the sum of n equals 0 to infinity of the entire quantity 5n minus 3n cubed divided by 7n cubed plus 2, all raised to the nth power. So the fact that this entire rational function is raised to the nth power tells us that we should use the root test. So we're going to set up the limit as n approaches infinity of the nth root of the absolute value of 5n minus 3n cubed over 7n cubed plus 2. All of that is to the nth power in absolute value bars. Well, here we are going to have this quantity being raised to the nth power as a positive quantity. So I'm going to go ahead and drop that. So the limit as n approaches infinity. So I'm going to drop the absolute value bars. This is 5n minus 3n cubed over 7n cubed plus 2. And then this is to the nth power. And then instead of writing this as a nth root, this whole thing can be thought of as being taken to the power of 1 over n. So I'm rewriting an nth root as to the 1 over n. So now n and 1 times n, this is like n over 1, this cancels. So now I'm just doing the limit as n approaches infinity of this rational function 5n minus 3n cubed over 7n cubed plus 2. So since the degrees here match, this is going to converge to negative 3 over 7, which is a quantity that is less than 1. So we know that this converges by the root test.